Right, okay guys. A couple of students have been asking about Anchorage zone design and deflection so they can finish off their project during the lockdown. And I've been giving a few lectures over WhatsApp and so on, but quite an increasing number of asks, so I'm just going to put a quick video down and we can do this. So lecture 6, once you've got lecture 6 behind you, you can actually finish the project. The only thing from lecture 7 you need is the typical details that you can do a drawing, but you've already got that. That was put on the Moodle site, and you can just copy that. Right, Anchorage zone, we'll do that quickly. Right, two things we need to look at, and I'm going to draw you some sketches here. It's a typical end zone elevation of an end zone, and if we have two anchors like that, we have an immense amount of force going onto each of these anchors, very high stresses, and they want to cause this sort of tension happening there. Anchors want to pull apart, and they want to split between the two and burst apart. Okay, that's the one thing that happens. The other thing, if you just zoom into one anchor, typically like that, and we just look at one particular anchor, very intense forces on the back there, well, the force going into the anchor, very intense stress all around the anchor, wants to cause this anchor to burst outwards as well. So we have to design for both of these things, and we just need to get through some of the nomenclature just to get you going. I'm going to just flip through the first few pages. You can read this yourself, but I just want to go through some things we need to learn, some terminology here. If we look on the bottom of page 3, the important thing here is the stress diagram of the application of the pre-stress force and the depth to which it's effective in the end block. So we're seeing the reference to things called YO over here, if you see that there. The YO being the depth of the block that is being affected. They describe YO here at the top of page 4. YO denotes half the end block dimension. Now I'll explain that to you. Let me just exaggerate the sketch here. I'm going to do an exaggerator on. I'm going to show an anchor exaggeratedly low on the beam. Okay. And that is the depth from the nearest edge of the beam to the center of the anchor over there. Okay. Now that would have been half YO. Okay, so now if we go to a full YO up like that, this would be YO, because here on page 4 it says YO denotes half the end block dimension. So sorry, that's YO, this is 2YO. Okay, so if we look at this stress diagram here, our stress is affected from a 0.2 YO to a depth of 2 YO along the beam. So if that was our 2 YO there, the effective area is there. So this is our area now where all our high stresses are taking place. Okay, if the anchor was in the middle over there, then 2 YO would be the whole height, and a greater area would be affected. Okay, what it means then is the further away from an edge, the further the spread of the rebar, and so the rebar becomes a bit less condensed. But we'll get there now. But as long as you understand, so that the distance, the YO distance, is from the middle of the force from the anchors to the nearest edge. That is YO. If you've got more than one anchor, it'll be the middle of the group of anchors. Okay, to the nearest edge. That's YO. YPO. We need to know YPO if we look over here. Okay, denotes half the anchor dimension. Now once again, if we look at a beam like that, and then we have an anchor like that, that there would be 2YPO. Okay, so half the anchor dimension over there would be YPO. Okay, we just need to remember this, and we need to park it because we're going to use that in the calculation of our bursting forces. If we have a group of anchors like that, okay, then our YPO, or actually we should sort it out, 2 YPO is actually the outside dimension from outside to outside of the anchor group. Okay, so YPO would be half of that dimension. Okay, so we just need to remember that. Right, let's just run through this example over here on page 5. Okay, so typically on this example, we've been given, on this example, we've got 2 anchors, both of 2,500 kilonewtons. The center of force is at 550 from the nearest edge, which is at the bottom. Okay, the anchors are 300 millimeters apart. Okay, very simple. So the first thing we need to look here, YO is the distance from the center of the anchor to the closest edge. So there, YO, distance from the center of the anchor to the closest edge, 550 mils. YPO, half the combined anchor dimensions. So here's your combined anchor dimensions at 300. Okay, plus half an anchor plus half an anchor. So 300 plus 250, the anchors are 250 square. Divide that by 2, because it's half the combined dimension. That's 275 millimeters. Now, if we refer to table 37, YPO over YO, we need to know that. So that is 275 over 550, 0.5. If we refer to table 37, YPO over YO, 0.5. The F bursting over PK is 0.17. Okay, let's come back to here. I've shown that already. Let's go to page 6. PK is the force at our anchors. We've got 2 anchors of 2,500 kilonewtons each, so our PK is 5,000 kilonewtons. Very easy then to reduce force bursting, which is then 0.17 times 5,000 kilonewtons. It's 850 kilonewtons. Right, the rest of this is very similar to a shear calculation. What we need to do is work out the ASV over SV in accordance with the reinforcing formula. I'm just going to go back to this page over here. The reinforcing formula, ASV over SV, is our force bursting over 200 times 2YO minus 0.2 YO. I'll explain this in a minute. So our ASV over SV for this example is the 850 kilonewtons that we calculated there, times 10 to the 3, I brought it to newtons, divided by 200. The 200 is the working force of the reinforcement. Remember, we're working at serviceability, so it's the serviceability strength of HT steel, and we're assuming that at 200 MPa. So use 200 MPa. Right, the 2YO to 0.2 YO. Once again, if we go back to where I discussed here, the area, the zone to which we're working is our effective end block. So it goes from 0.2 YO to 2 YO. This once again is with reference to our diagram, our stress diagram, where you can see the influence of the stress taking place from between 0.2 YO to 2 YO. What that tells us is this reinforcement that we're going to design here is going to be spread between 110 to 1,100 millimeters from the anchor. And let's look at this reinforcement calculation. Typically, we're going to do a first trial with 2 legs of Y16, 402 millimeters squared. So if we take our ASV over SV equals 4.29, then SV is 402 divided by the 4.29, 93 millimeter centers. So our spacing of our bursting links then is Y16s at 93 millimeter centers. Let's say 90 millimeter centers. And they'll be spread from 110 to 1100 millimeters from the anchor. 110 being 0.2 YO to 1100, 2 YO from the anchors, i.e. from that point to that point, 110 to 1100, we've got 12 Y16s at 90 centers. Notice the stirrup that we're using is very similar to a normal shear stirrup, shape code 60. It's a closed stirrup, and that's going to design our rebar required for this bursting of the anchors, to stop them from splitting apart at this point. Okay, the exact same thing is going to happen as we saw there. The exact same thing is going to happen in the other direction as well. I'll just redo another sketch. We've got our 2 anchors sitting here like this for this example in the book. Right, now we've already designed for the bursting, pulling those anchors apart. But now if we turn this through 90 degrees and we just look at one of the two anchors, okay, and we look at the end view of this. Let's look at the end view. So there's our bottom anchor, there's our top anchor in the end view. We basically are going to do exactly the same thing, but with different values. There's our 2YPO, and there is our YO. I just want to check those values again. Is that what I said? YPO denotes half of the anchor dimension. So yes, that's 2 YPO, and YO denotes half the end block dimension. So that is correct. Yes. Okay. So basically, we're going to do the exact same procedure again, but this time just for a single anchor. So PK is going to be only 2,500 kilonewtons. Okay. Your 2 YPO over 2 YO is going to be 250 over whatever the width of this example was. I forget what the example was. It's that it's 400 wide. So you're going to take this 250 over 400, and that'll give you whatever the figure is that you take to table 37, is it? Yeah, table 37. And you'll get this force bursting over PK again. And so you'll design a similar sort of thing, but these we put as clips that go around the anchors like that. So you'll design as, you'll only need to design one, but you'll put the same rebar around each clip. At this point, what I must say is that quite often this reinforcement that we're designing here often comes with the anchor. You'll see sometimes an anchor is delivered to site and it has this coil already welded to it. That is this steel. We can do one of two things. We either take the coil off and use our steel, or we can just leave the coil on and abandon our steel, or we could put the coil and our steel in, which quite often we just do that. We put both the steel. But you can go ahead now and you can design this this bursting steel for your project, both in the vertical and in the horizontal direction, quite simply. Before we do that though, I just need to discuss one thing with your project. I'm just going to draw it a very typical example of the beam that we've got in the assignment. It looked a bit like that. Okay, there's our neutral axis, for instance. Right, and now most people have come to me with the question of what to do at the end block for the project, because most cases we've got at midspan, we've got three cables, and that's their position at midspan, so you've got maximum eccentricity. But now at the end, we don't have enough space to fit in 3 anchors next to each other. The beam is only 900 wide. We need a meter to put 3 anchors next to each other. So what we do is we put the middle anchor on the neutral axis. We can put one of the others above it, and we can put one of the others below it at the end of the beam. Obviously the middle anchor will travel down to midspan to this position. One of these will travel down to this position, and this one will travel down to that position by the time it gets to midspan. And then of course it will duplicate the same to go to the other side of the beam, where it will end once again in a vertical alignment like this. While I'm thinking about it, don't forget that this doesn't happen only around the live anchors. It must be something that happens around both ends of the beam. The dead anchors also will want to burst in exactly the same way. Okay, so follow this procedure. Do this for your project. You can have 3 anchors. Just another little aside that I must discuss with you here. All I'm expecting you to do for your project is to design the force with all 3 anchors as if they were all stressed fully at the same time. Now obviously that doesn't happen in practical purposes. It can't happen, but I'll show you what we do in reality. What we would have done is we would have taken the force on the first anchor, the second anchor, and the third anchor separately. For instance, we would have had to check just the force of that using this YO. Then the force, then we would have to design what sort of reinforcement we would need in that area. Then we would check if it's got 2 anchors, and we would have applied that force into a larger area. And we would have needed to see what reinforcement we need there for just 2 anchors being stressed. Then if we stressed all 3, and of course a larger YO, what would the reinforcement be required for that with all 3 stressed simultaneously? This is almost always, with all 3 stressed, the way I've just shown you, is almost always the governing case. But if you do find that 1 or 2, the bottom 2, or necessarily they're not just the bottom 2, it could have been the top 2, if just some of them are stressed and you get greater steel, then you would have to supply the steel for that case. But I just want you to know that, but you don't have to do it in the project. I just want you to do the case with all 3 stressed. Okay, let's just pause it there, and then I'm going to go on to deflection in a minute.